Hi everyone, this is Mrs. GA, and today we're going to be graphing logarithmic functions. Okay, I have a quick warm-up for you guys, so if you could please pause the video and give this one a try. We can check your answers in just a few moments. All right, go ahead and check your work here. So remember, logarithms define exponents. So if you have the common log of 1/10, this first x value, and remember this is common log, it has base 10 even though we don't write it. You're essentially saying 10 to what power is 1/10, so -1. 10 to what power is 1 must be 0, and 10 to what power is 10 must be 1. So same idea for the natural log. Remember, a natural log is a logarithm with base e. We write it like this. We read it as natural log of x. So if the value here is 1 over e, the exponent must be -1. If the value here is 1, the exponent must be 0. And if it's e, the exponent must be 1, because e to the power of 1 is e. So I plotted both of those. Here, you kind of have to approximate, of course, do your best. But you can see blue is f of x and red is h of x. So a few things to note here for the domain and range. You can see that the domain is restricted for both. And we know that in terms of this number that's inside the logarithm, it will never be 0 because you can't take a base, raise it to a power, and get 0. And it will never be negative because, again, you can't take a positive base. And by definitions, all logarithms have a positive base. You can't raise it to any power and get a negative answer. So our graphs will actually never quite touch y equals 0. So there's actually a vertical asymptote here. I'm sorry, at x equals 0, not y equals 0. And so that can help us to define our domain. So our domain for both parent functions is simply 0 to infinity. And again, it will never touch 0 because that wouldn't be possible in terms of logarithms when you're evaluating them. And then the range is going to be all real numbers. Although this looks like it's pretty flat, it is still going to grow slowly, but it will eventually reach all real numbers for the y values. So you can see from the warm-up that even though there were two different base logarithms, many of the features were about the same. The shape was the same. The domain and range are the same. All parent functions for any base logarithm share a lot of the same features. Of course, we have to adjust for the points depending on the base, but all parent functions will have a domain of 0 to infinity and a range of all real numbers. And here again, 0 is not included. For the end behavior for the parent functions, as x approaches positive infinity, our graph is slowly but certainly going up. And then on the left, for end behavior, well, x isn't actually approaching negative infinity. X is approaching 0. And you can see from the warm-up, as x approached 0, so that's what's happening on the left, f of x approaches negative infinity. So our graph went down. For asymptotes, we only have vertical asymptotes. And for, again, the parent function, it's at x equals 0. For intercepts, they will all go through that point 1, 0. Of course, again, I keep repeating this. This is for the parent function. If there's some sort of shifts going on, then that could change. Our graph is positive to the right of our intercept. You can see that's where our graphs crossed over. So it's positive from 1 to infinity, and it's negative from 0 to 1. So again, from between that vertical asymptote and where it crosses the x-axis. And then our graph is increasing, not over all real numbers, from 0 to infinity. So it's always increasing, and our parent function is never decreasing. So these general features can be applied to the parent functions of any base logarithm. So today when we are graphing, we can use transformations to help us graph these functions. So here's maybe like a transformational form, I'll call it, of our logarithm. We can apply this to any base. I just have the common log for this one. So we know that if there's a negative out front, that causes a reflection over the x-axis because it's a vertical reflection. we know that if there's a value that's being multiplied to the front, we would call this a vertical stretch or shrink. And it's going to be by a factor of whatever that number is, so by a factor of a. Now, if you have a negative on the inside, this would cause a horizontal reflection, which is over the y-axis. If you have something multiplied to x, notice that it's factored out from this binomial. If there's also some type of sum or difference, you have to factor it out first. This would be a horizontal stretch or shrink. This one you have to be careful because it's by a factor of the reciprocal. So it's by a factor of 1 over b. This h causes a horizontal translation, so a shift left or right. And the k causes a vertical translation, so a shift up or down. So again, you guys know these. They're the same general rules for any type of function. Today we're just going to apply them to our logarithmic functions. So I recommend that first you think about your parent function and you find at least 3 good reference points, and then you make a t-chart and transform those coordinates according to what you see in your equation. All right, let's try one together. So we're going to graph, find the domain, range, x-intercept, asymptote equation, and at least 3 exact coordinates. So we could see here that our parent function is a base 3 logarithm, log base 3 of x. So we could take we could find 3 coordinates from our parent function. A good one to always do is 1. So we have 1, 0. Because 3 to the power of 0 equals 1. We can even do, in this case, 3, and then our y value would be 1, because 3 to the power of 1 is 3. And for this one, we could even do 5 if we wanted to, or sorry, 9. 9 would be a nice number to use, and then our exponent, or the y value, would be 2. So notice that I'm picking nice numbers here, so I don't have to, do any decimal approximations when I don't need to. So you get to pick the x values, your reference points, pick nice numbers. So then looking at the transformations in our function for f of x, I see the reflection over x-axis, which is vertical. I see the vertical stretch by 2. And then we see the translation up 4 units. So all 3 of these transformations are actually vertical transformations. So our x value is going to remain unchanged from our parent function. And for the y values, we'll multiply them all by -2, and then we will add 4. So again, these will stay the same. And then these we can adjust. So this becomes 4, this becomes 2, and this becomes 0. Now another thing to consider before I start graphing is our asymptote. So we know for the parent function, our asymptote is at x equals 0. Since that has to do with the x value, this would be affected only by a horizontal shift, so if you're shifting left or right. So since I'm not shifting left or right, my horizontal asymptote is actually just going to remain at x equals 0. So I'm going to start by drawing that in, and I can write the asymptote equation here, because that will help me when I'm sketching my graph, so I know to follow along the asymptote. And then we could plot the points that we found with our transformations. And then 3, 2, and 9, 0, so right here. And then since we do have that vertical reflection over the x-axis, it makes sense that our graph is now looking like this. So now it's a decreasing graph instead of an increasing graph. And there we go. So you can see that our domain is still unchanged, and that's because we didn't have any shifts to the right or left. Our range is still all real numbers, and our x-intercept is at 9, 0. All right, let's try another one together. So when we're working with a natural log, we are going to be providing exact coordinates, but then we'll also need a decimal approximation to help us plot those points. But we'll start by keeping everything exact. So our parent function again is natural log of x. So we can get a couple points from our graph. So we can always start with 1, 0. That should be for any base. You should always do 1, 0 because any base to the power of 0 will equal 1. And then here we can do e1 because e to the power of 1 is e, and we could even do e squared because e to the power of 2 is e squared. And then we can take these coordinates and transform them. And I know it's weird to leave it with e and e squared. We are going to do that in our t-chart as well. We'll leave it with e and e squared, but we'll also provide a decimal approximation. Now looking at our transformations, you can see that there's something we need to do first before we decide how to transform. We do need to make sure that negative on the inside of our logarithm is factored out. So we do need to write it like this. So this has a vertical shrink by a factor of 1/2. And then we also have a horizontal reflection, so that's a reflection over the x-axis or the y-axis. And then we actually are going to translate to the right 3. So remember, it's always the opposite of what you see here. And you can see that if we didn't factor out this negative, because any multiplier here does need to be factored out, you would tell me that this shifts to the left, but it actually shifts to the right. So make sure you always look for that and do this first if you need to. So there are 2 horizontal transformations. So we'll do negative x. And then if I want my graph to go to the right 3, I'm going to add 3 to the coordinates. And then I'm going to multiply all my y values by 1/2. So I could do that first, like this. And then the way I'll write this, well, for this one, we can just use our numbers. So negative 1 plus 3 is 2. Here, we can just write this as negative e plus 3, and I'll get a decimal approximation for that in a moment. And then negative e squared plus 3. So we can plug those into our calculator and get decimal approximations. 1 second. So this one will be approximately 0.28. And the next one will be approximately negative 4.39. So here's the exact coordinates, which I definitely want. But again, we will need the decimals to help us plot the points. Now, another thing to consider, again, is our asymptote, which was at x equals 0. But since our graph has been shifted to the right 3, I can actually just add 3 to my asymptote. And so now it's going to be at x equals 3. So the first thing I like to do is sketch in the asymptote because it will definitely help me when I'm graphing. And then we can plot the points that we have. So we have 2, 0, and then we have 2.8 or 0.28, 1/2. So again, you kind of just have to estimate for that one. Or change the scale of your graph, to make it a little easier, but either way is fine. And then we have negative 4.391. So like this. And then knowing that our graph is going to follow along our asymptote, we can sketch in a graph that looks like this. So you can see why it's so nice to have that asymptote sketched in before you start actually drawing your graph. And again, now our graph is on the left side of our asymptote because of that horizontal reflection. So you can see now our domain is actually from negative infinity to positive 3. Our range is negative infinity to infinity. And our x-intercept is at 2, 0. If you ever need to find an x-intercept, like if it's not one of the points from your transformed coordinates, you can always just set the y value of your equation equal to 0 and solve. All right, so at this point, I'm going to ask you to pause the video and give this one a try on your own. And you can hit play when you're ready to check. All right, go ahead and check here. Since it's a common log, I picked the x values 1/10, 1, and 10. I didn't pick the x value 100 just because it seemed like it'd go way off our graph, but you could and just rescale your graph. And then you can see that there's a vertical stretch by a factor of 3, and then it shifts left 2, down 5. So there's only one horizontal shift to the left 2, which also shifts your asymptote. And then we multiply our y values by 3, then subtract 5, giving us these 3 exact coordinates. And then I think the trickiest part of this one is probably finding that x-intercept. So you set y equal to 0, and then you solve. So you can isolate your logarithm, and then if you rewrite it, you get 10 to the power of 5/3 equals x plus 2. So you could subtract. And then I simplified this to 10 times the cube root of 100, right? Because it would be 10 times the cube root of 10 squared minus 2. So this would be the exact coordinate. And then approximately that's 44.4. So it goes way off our graph, but we're still able to find it. All right, I have one last one for you to try on your own. So again, please pause the video and give it a shot. All right, go ahead and check your work again here. So here's a couple coordinates from my parent function, which is the natural log of x. So these are the x values I picked, but if you want to pick like 1 over e, that would be fine as well. And then we have that reflection over the x-axis, and then our translation up 6, which are both vertical transformations. So our x values are unchanged, and then for our y values, you multiply by -1, then add 6. And I have the decimal approximations here just to help me plot my graph. So you could see that our asymptote was unmoved because we didn't shift left or right. Our domain and range are unchanged for that same reason. And then to find the x-intercept, again, you just set y equal to 0 and solve. And you can rewrite this as e to the power of 6 equals x. So here's the exact coordinate. You could write it as e to the power of 6, comma 0. But just to give you an idea of where that would fall, that's approximately 403.4. So again, it's way, way, way off our graph. But again, we're just providing the exact coordinate here. Okay, that is all for today's video. Thank you so much for watching.